Good morning or good evening from Silicon Valley, where I'm from. Thank you for being here for this presentation. I'm going to talk this morning about eliminating bias in the deployment of machine learning. Now, the reality is we're not really going to eliminate bias, but we can at least reduce the impact of bias. So we'll talk about why this is important and how to go about making it happen in your environments. Now, one of the problems is the perception is around deep learning is some kind of AI magic, that we pour a bunch of data into a black box and then we pull out answers like a magic rabbit coming out of a magician's hat. The reality, of course, is that AI is really just math, right? We're using mathematics and probabilistic statistics in order to classify and predict the future. We're going to take deep learning with multi-layer neural networks and teach the algorithms how to classify patterns and make predictions based on statistical methods. Now, because these are statistical methods, they are probabilistic. They cannot always be perfect. They cannot always do the same thing in exactly the same way. And that's kind of the point of learning. Each time you ask for an answer, you will get a different response. So when we look at the development of these algorithms, the idea is that if we use math instead of humans to make decisions, we should eliminate bias, because humans make decisions on subjective basis, but math is deterministic. So we should be eliminating bias, truth or fiction. Well, the reality is we will reduce bias because the mathematical algorithms will certainly have less bias than human decision makers. But the point is that humans are still involved in creating those algorithms, so there'll still be bias that can be introduced into those algorithms. I think that the mathematician Cathy O'Neil does a good job of describing the dangers of these algorithms embedded inside these black boxes. She wrote a book called The Weapons of Math Destruction. Cathy herself is a mathematician, and she spent a lot of time teaching and doing research work at places like UC Berkeley, Harvard, MIT, Barnard, Columbia, some of the best universities in the US. And she observes that inside these black boxes, there's a lot of bias and discrimination, but it's often hidden. And so it's important to be able to expose the possibility of bias so that we can manage this bias in an appropriate way. The World Economic Forum published a report stating that ethics and perception of bias are the #1 reasons why we are inhibited in widespread adoption of artificial intelligence. There are more than 180 different types of human biases that have been identified, and some of these biases will come into the algorithms that are developed by humans. I'm going to discuss a few of them based on the time that we have, and some of the most common ones that can cause problems when you're developing AI algorithms and deploying them in a commercial or government setting. And the important point here is to recognize that bias does not originate in the AI algorithms themselves. Bias is sourced from the humans that build those algorithms. So we want to understand how that happens and how we can prevent or at least reduce the impact of this bias that humans introduce into AI algorithms. First, let's talk a little bit about the difference between bias and variance. So in front of you, you have 4 different targets, and I think it's very important to understand the difference between bias and variance, because variance is a natural consequence of using probabilistic algorithms. If you look at the bottom left-hand target, we see that the model is very, very good. It is hitting the target every single time. Now, it's not exactly in the same place, but it's within the target zone. Variance is small. Bias is also small. We're really right on target every time. On the bottom right, we see that we have a higher degree of variance, but it's a random error in prediction. We don't always hit the target, but sometimes we're to the left, sometimes we're to the right, sometimes we're up, sometimes we're down, and there's no bias in the bottom right-hand target. Our model is not perfect, but it's not biased. In the upper left-hand corner, we see that we're actually hitting the same zone every time, but it's not actually on target. So the variance is very low, but the bias is actually quite high. So you can imagine that if on the bottom right-hand side, that dimension is, let's say, gender, it means we may be biasing against gender. We may be declining loans for females in favor of males when really we should have been on target giving more loans to females relative to their male counterparts. This is an algorithm which is very consistent. It's got low variance, but it's high in bias. So this is very bad. To the upper right-hand side, we also see bias, but the bias is coupled with higher variance. But you see that the target is almost always to the left of where we're actually hitting with the model. So again, you can imagine that there's bias towards one side of the target that we're introducing into the output of these models that we have created. Variance is okay as long as it's not biased. Of course, we like lower variance because that's lower error, but bias is much worse than variance when we think about the impact on humans and the ability to avoid discrimination. Now you might think to yourself, oh, no, my model is okay because I'm not going to include the variables like gender or race or religion or sexual preference. I'm not going to include those variables, and therefore the model can't be biased because we're not giving the model that data on which to make its prediction. Well, this is a bit of a fallacy in thinking, because the reality is if you look at, let's say, purchase patterns, which I'm sure you would include in your model, I can examine purchase patterns and I can determine with very high accuracy whether the person doing the shopping is male or female. I can look at clickstream data and I can tell what is the sexual preference of the individual. So even data that is not directly the attributes on which bias might be based can be derived through correlation. The mathematical probabilistic algorithms will find the patterns in the data, and even though you did not intend to have a model that was biased towards race or gender, it might happen due to correlations that are inherent in the data that you're using as your input data set. Because of the concern over this phenomena, in academia a few years ago, the Association for Computing Machinery created a workshop of practitioners and academics that are focused on this issue, which is shortened as FAT. FAT is an acronym that stands for fairness, accountability, and transparency. So we want our algorithms to be fair. We want the people that create and deploy the algorithms to be accountable for the outputs of those algorithms. And we want transparency, so it's very clear exactly what's going on inside those algorithms. In the EU, early policy and law associated with GDPR, the General Data Protection Regulation, has been put into place. In California, where I'm from, earlier this year, we put into place the California Consumer Protection Act, the Algorithmic Accountability Bill in New York City, Personal Data Bill in India. In Russia, there are similar laws and regulations that make it illegal to have bias in your AI algorithms. Well, it's relatively easy for a politician to write such a policy or a law, but how do you enforce such a law? How do you detect that there's bias in the AI algorithm? Well, this is very, very complex. And people hypothesize that we will need AI solutions to monitor AI solutions for bias. But who's going to monitor the AI solutions that are doing the monitoring? So we get into this recursive problem, and it's very difficult to solve. Now, when we look at the General Data Protection Regulation, and if you look at Article 22, one of the rules is that any human has a right to have another person in the loop for decision-making that impacts themselves. So if we have a decision-making algorithm that is determining whether I get a line of credit or whether my actions are fraudulent or anything that impacts me, we can have a human in the loop. Very often we think AI stands for artificial intelligence or automated intelligence. In this case, AI stands for augmented intelligence. In other words, the human and the machine have to work together, and the human has to be able to deliver an explanation for why a decision was made related to the person that it applies. So my claim is that the mathematics and the AI algorithms are not inherently biased. It's the data that you use to create your AI algorithms where the bias is sourced. And so we need to pay attention to the data supply chain for the training sets that are used to create the AI algorithms. In the end, your solution is only as good as the data that you put into those solutions. So I want to talk a little bit about some of the biases that get introduced as these training data sets are created. One of the most common sources is selection bias. In the end, it is a human that chooses the data that is used for the training sets. The data scientist will gather data from different sources, and if the source of that data is biased, then we are going to have bias introduced into the training set, which is then going to translate into the algorithm. So for example, I might be an academic at a very prestigious university, and I'm developing an AI algorithm, but I need to collect training data. So I will encourage undergraduate students to come and participate in an experiment, and we will collect the data from the behavior of those undergraduate students. The problem is that those undergraduate students are not necessarily representative of the whole population. So now we're going to take a model that was built with a training set of these very highly academic students, and we're going to apply it to the general population, and the behaviors are not necessarily the same. So the academic did not intend for bias to be introduced. The academic went to a reasonably accessible source of behavioral data by measuring undergraduates at the university, but the problem is there is bias that has been introduced. And once we have the data, how we choose to manipulate the data, what data we discard as outliers can also be a problem. So a data scientist will examine the data looking for missing values, looking for outlier data, and if you exclude certain outlier data, that might actually be excluding the behaviors of certain populations within the general people that you're meant to apply this scoring algorithm to. And when you have a population which is small in size relative to the full population, so if there is a minority population and you don't have a large enough training set, then the algorithm may not be able to determine and accurately predict the results for this minority population. And this is especially true for multi-layer neural networks because the dimensionality of the data is very, very large. So the possibility of having sparsity in the training set is very high if you don't have a large enough data set used to do the training. This is a very visible example of what might happen if you are introducing human bias in the exclusion of certain data from the training set. So in this case, we have a self-driving car. This car was trained with lots and lots of data collected from lots of vehicles, and the data scientists decided that fire trucks are not good sources of training data because fire trucks, when they're on the road, their sirens are on, and the fire truck is going in and out of all the cars and driving very crazy. And we don't want our self-driving car to learn how to drive from a fire truck because these are very erratic driving behaviors and we don't want them. So we can then exclude fire truck data from the training data. And then we teach our self-driving car how to drive. But in this particular case, when the self-driving car encountered a fire truck and had never seen this kind of crazy driving behavior and didn't know what to do, it ended up rear-ending the fire truck because the data was excluding the crazy behavior of fire trucks, so the self-driving car didn't know what to do in this situation. So excluding outliers, even though the fire truck is clearly outlier in terms of driving behavior, can have some pretty serious consequences. Stability bias is a bias that results from the data scientist getting a data set used for the model training and keeps on using the same training set. Now, the reason this happens is because it's a lot of work to create the feature set used to do the training on a model. So once I have this source of data, I've done my data quality work, I've validated it's a good source of data. Once I get it and it's working, I don't want to change that data set because it is a lot of work and there's never enough hours in my day and there's never enough days in the week, and I've got a big backlog of models that I've got to train. So once I get a data set that works, I'm going to continue to use it. And this is made even worse in some industries which are highly regulated. For example, in banking, if you change the data set, if you change the algorithm, the regulators are going to want to come in and do a full audit. And this can take weeks or months and a lot of effort. So the incentives are to get a data set that works and to keep using that data set. If it's not broken, don't fix it. The problem is that data sets, when you don't evolve them, they become stale. Effective learning stops because you're not inputting new data and you don't have new opportunities to learn. And this relates to another kind of bias, which is called emergent bias. So predictive algorithms learn from historical data. But when context changes, if we're still using the old data, we're not understanding that there are new behaviors, new possibilities that have been introduced, but because we're using this stale training data, we don't see it. Consumer behaviors change all the time. If you think about recommending a song for someone to listen to, the songs that you would recommend 5 years ago are not the same songs that you would recommend today. In fact, the songs that you recommend 5 weeks ago are not the same songs you would recommend today, because there are new songs being published every day. Consumer tastes are changing all the time. Medical treatments are changing all the time. It might be that there was a life-saving treatment that was invented last week, and if the AI algorithms is based on data from last year, we're not going to consider this life-saving treatment, and the patient is not going to get the best healthcare possible. New laws happen all the time, so when the rules change, the training set and the outcomes that we're training against also have to change. So emergent bias and stability bias are often kind of treated together, but we need to understand that we need new data so we can continue to learn all the time. Don't let your data go stale on you. The last form of bias that I wanted to talk about is the bias that is inherent in biometric data. And I'm going to give you a few examples, but there are many, many examples. And in almost all cases, this is a lack of sufficient training data. One of the most infamous examples is the image recognition algorithm of Google, who's one of the most sophisticated in doing machine learning. It was identifying gorillas instead of African Americans when you saw a picture of a human. This was because the training set did not have enough data to allow it to distinguish between these two kinds of entities. So they did not have enough African Americans in the training set, and probably had a overabundance of gorillas, and it caused a problem in the predictive algorithm. Ironically, Nikon, which is a Japanese camera manufacturer, had a bias in its cameras where one of the features of the camera was to tell the photographer if someone in the photograph that was just taken was blinking, and to suggest that they should take the photograph again because someone had their eyes closed. And interestingly, the algorithm, which was identifying or classifying a person as having closed eyes, had a bias towards Asians, suggesting that those Asians had their eyes closed when they really didn't. And this is ironic because, of course, Nikon is a Japanese manufacturer, and the Asians have a slightly different eye shape, and the algorithm was mispredicting or misclassifying closed eyes with Asian eyes. Now, I suspect that the training set that was used for predicting the blinking of the eyes was actually not taken from a largely Asian population, but probably somewhere, for example, in Silicon Valley, which, yes, of course, there are Asians, but the vast majority of people are of European descent or perhaps Indian descent. And so the eye shape was not sufficiently represented for Asians, and we had these false positives classifying blinking eyes when there were no blinking eyes. Speech recognition also has high correlation to certain ethnic accents, where for some accents, the speech recognition is very bad, and for other accents, it's very good. And this, again, depends a lot on where was the training data set for the speech recognition source, and were we representing all of the ethnic accents in a way that provided enough visibility to the algorithm to get accuracy for its translations. We often see that the AI algorithms amplify human bias. For example, in this case, we see that the algorithm was very good at identifying kitchen utensils. It could tell the difference between a spatula and a spoon and a knife, but it didn't do a very good job in telling the difference between a man and a woman in the kitchen. This is because of bias that was introduced in the training set. Because there is bias that women should be in the kitchen, men should not be in the kitchen, the training set had more women in the kitchen, and the algorithm then saw that pattern and then misclassified males in the kitchen as females, even though arguably classifying spoons and spatulas should be harder. Because the training data was better, we were able to more accurately predict utensils than gender of the person in the kitchen. Similarly, there are patterns picked up if you look at the algorithms used to do sentence completion when you are typing an email. If you mention CEO as the subject of the email, the default patterns of completion will go to pronouns such as he and his rather than her and hers. And this is because there's a bias that assumes that CEOs are male more than female. The fact is, if you look at all CEOs in the United States, there are many more male CEOs than female CEOs. So the algorithms picked up that pattern, but then inadvertently did sentence completion, assuming all CEOs are male, which is not correct. Profiling successful employees. There's an infamous example where Amazon was using AI algorithms to screen resumes. And the resumes had gender removed and the name of the person removed, so there shouldn't be any way to say the difference between a male and a female. But the algorithms are smart, and they can see that actually females write their resumes different than males write their resumes. So even though the names were not there and gender was not there, the algorithm still picked up on the difference in how the resumes were constructed. Women, for example, talking more about collaboration and teams, men talking more about themselves and winning and so on. There are certain verbs and certain phrases used more by females than males, and the algorithm picked up these patterns. And because there were not very many female employees within Amazon, that built-in bias got reinforced in selecting resumes that were more like the people that were already in Amazon, which were male. Now, Amazon eventually discontinued the use of this algorithm because, of course, they did not want bias in their hiring practice. This was not something they did on purpose, but it happened nonetheless because the mathematical statistical algorithms will find those patterns. In the end, the algorithm is only as good as the data that we use to train it. The problem is that if we put this data into the black box and we do the training and we build a multi-layer neural network, the algorithmic authority that is aligned to the fact that there's this very sophisticated technology means that the person who receives the decision thinks that it's correct. They believe that it's correct because the computer said it was true, so it must be true. But this is not really the case because there's still humans involved in building the algorithms. And we need to recognize, and I will quote Cathy O'Neill here, that algorithms are essentially opinions embedded in code, because the person who built the algorithms will have bias that gets introduced by the data they select and how they manipulate that data as it goes into the algorithms. So we need to take actions in order to minimize the impact of prediction error. For example, we should use stratified sampling and optimize observation weights to make sure that we are recalibrating when the training set doesn't have a good sampling across all different populations. So we can recalibrate to use sampling in a more effective way. We need to analyze missing values for some systematic bias to make sure that the missing values aren't associated with a particular trait that are easily correlated. So for example, if you ask for weight, the number of kilograms that someone weighs, it is likely that most males will fill in that field, most females will not fill in that field. So that missing value then becomes a correlation to gender in this particular example. We need to standardize processes and create templates for model documentation and deployment. Now, I'll tell you that a lot of data scientists don't like this suggestion. They believe that data science is a creative process and you should not standardize a creative process. Well, I'll tell you that the second word in data science is science. Science means repeatability. Science means that we're using scientific method. And so it should not be a process which has too much randomness introduced. And when I say randomness, it's actually bias in that randomness introduced by the human. So standardizing processes is very important to reduce the opportunities for bias. I would also suggest that in your machine learning teams, you should have a challenger team, a team that is going to examine the algorithms and look at the opportunities to see, has there been bias introduced? Because data scientists, when they're working together and they discover something great, they want to be very proud of it, and they should be proud of it. But it becomes this group think where you have essentially an effect which is called confirmation bias, where the team believes they're moving forward and they don't think of the fact that there might be bias in the algorithm. You need to have an independent team that is monitoring for that possibility. So when we look at the places where bias can be introduced into the AI solutions, I'm going to speak to three different areas. We'll talk about framing the problem. So in other words, what is the problem that I'm trying to solve? Let's say that I'm building a music recommendation algorithm. Now you, as the listener of the music, you might think that the purpose of this music recommendation algorithm is to choose the song that you most want to listen to at this very moment. And I will understand that the songs that you listen to on a Friday night are different than the songs that you listen to on a Sunday morning. I will understand the preferences for each individual based on the songs that they've listened to in the past and which songs they completed listening to and which ones they skipped the next song. And so a song recommendation algorithm can be used to choose the best songs for a person to listen to at any given moment in time. But what is really the goal of the algorithm? Maybe the goal of the algorithm is to pick a song that you'd like to listen to, but there's another factor which might not be transparent to the person receiving the recommendation, that I want to minimize the royalties paid to the artist because I want to spend less money in my music recommendation system. And so I might recommend you a song which you would like a little bit less, but it's going to cost me a lot less royalty that I have to pay to the artist for the song. In that case, you're not getting your best song, you're getting the song that is good enough, that is the lowest cost song. And so it's important that there's transparency so the people receiving the recommendations understand exactly what they're getting on the other end. The places where bias can be introduced also include how the data is collected. So in my song recommendations, I might decide that people shouldn't listen to songs with bad words in them. So profanity and the 7 words that you can say on radio, we're not going to recommend any songs that have bad words in them. So now by excluding all of the songs that have profanity, I've now become the moral police. And again, this transparency that should be there. If you want someone to exclude those songs because your children are listening and you don't want to hear those words, that's fine. But there should be transparency. It should not be opaque that you're excluding certain artists and certain songs because you don't like the morality of that music. So how you frame the problem, how you collect the data, and how you prepare the data, and how you include or exclude outliers is very important to understand when making sure that we are not introducing inadvertently bias into our AI solutions. My suggestion to you is that you put into place in your organizations, whether they be commercial or government organizations, an algorithmic audit capability, that you audit the data integrity, you audit and make transparent the definition of success of the algorithm. For example, the monetary factor versus the preference factor in my song recommendation. We should also be monitoring the accuracy of the predictions, the accuracy as well as the bias that is in those predictions. So there's good news and there's bad news. Let me start with the bad news. The bad news is that the AI algorithms are as prone to bias as the humans that they're attempting to emulate. The good news is that these biases can be understood and managed. But we need to be proactive in doing that. We need to be proactive in managing the bias so we can successfully deploy AI without consumer backlash, where there is a feeling of unfairness or a feeling of lack of transparency. So my recommendations to you are to first start with a standardized approach for developing and deploying machine learning. Create standardized processes and templates for doing things in a consistent way. Identify prejudices that exist in the processes for collecting and processing the data that feed into your training sets. Test for unwanted bias that can be embedded in the algorithms. There are industry tests that you can run, produce commercially as well as in academia. Invest in explainability. A black box is not going to be good for the people that are receiving that recommendation. There are open source algorithms like Shapley that will provide explanation even of very complex mathematical algorithms that a normal human can understand. Continue and constantly monitor the performance of the algorithms and challenge your assumptions. In fact, have a challenger team that will challenge the assumptions of the data science teams. Thank you very much for spending this time with me this morning. Thank you.